All right, ladies and gentlemen, welcome to another exciting day in the world of chemistry. Today we're going to be talking about exceptions to the octet rule when forming Lewis dot structures to describe the covalent bonding within different molecules and ions. We already looked last class at an initial exception to the Lewis dot structure octet rule, which was in describing the bonding for hydrogen. Recall that because hydrogen is in the first period, it exists with electrons in the first principal energy level, and therefore a complete first energy shell represents only 2 electrons in the 1s orbital. Therefore, hydrogen is a stable atom as part of a Lewis dot structure molecule when it only has a single bonded pair of electrons. The remainder of our day today will focus on some other exceptions to these Lewis dot structure rules, and in particular, the next of those exceptions we're going to look at is a pair of exceptions to our Lewis dot structure rules which belong to beryllium and boron. Both of these species form what we call incomplete octets. An incomplete octet is an electron configuration which does not give a full set of 8 electrons to one particular atom. Beryllium and boron in particular have tendencies to form incomplete octets, in particular with very highly electronegative elements, because beryllium and boron have low electronegativities and are therefore unable to attract electrons towards themselves sufficiently in order to form a complete octet in certain molecules. The next species we're going to look at, which tends to exhibit exceptions to the Lewis dot structure rules, are phosphorus and nitrogen. Each of these two species typically will form stable compounds with odd numbers of electrons. And generally these are when phosphorus or nitrogen are bonded to more electronegative elements than themselves, and they end up taking a grand total of 7 valence electrons rather than a complete octet of 8. Beyond these examples, in addition, there's also what we refer to as an expanded octet. And that's the first problem we're going to have a look at here for the species XeF6. So we're going to go ahead and form a Lewis dot structure for this species. To begin with, just as before, we're going to start by counting the number of available valence electrons to form bonds within this molecule. Xenon, a noble gas, has a total of 8 electrons in its valence shell. And fluorine, a halogen, has a total of 7 valence electrons. Recognizing that there are 6 fluorines within this molecule, that gives us a total of 42 electrons contributed from fluorine. And if we sum all of these electrons up, that gives us a net total of 50 electrons in the valence shell available to form bonds within our molecule. Now, as we go forth to the next step, which is to draw the skeletal structure for this molecule, we're going to go ahead and put xenon as our central atom in this species. This should make logical sense because xenon itself is a relatively large radius atom, and if we were to try and put a fluorine atom as the central atom, that would imply, number one, we would be forcing fluorine, the most electronegative element on the entire periodic table, to form a large number of bonds, whereas fluorine tends not to share electrons effectively. And number two, putting a smaller atom in the central position there would essentially force a large number of electrons into one particular region in space around that central atom, increasing the repulsion between those electrons and thus increasing the potential energy of our system. So again, we're going to choose the largest, least electronegative element to put in the center of our Lewis dot structure. And then around the outside, we're going to put 6 fluorine atoms. All right, having now put our 6 fluorine atoms around the outside of this central xenon, we can now go ahead and form single covalent bonds to complete our skeletal structure with 6 single covalent bonds, each of which contain 2 electrons. That uses up a total of 12 of our available 50 electrons to form those bonds, leaving us with 38 electrons remaining. With those 38 remaining electrons, we now need to go ahead and make a comparison to the number of electrons which we have available versus how many we need to complete our octets. With 38 electrons available and a total of 6 fluorine atoms, each of which still needs 6 electrons remaining to complete octets, That means at that point we can distribute all of those electrons as lone pairs and still have an extra 2 electrons left over, having completed all the octets for our atoms, which at this point leaves us with an extra pair of electrons which need to go somewhere. And we recognize at this point that we need to put those electrons in essentially one of two positions. They can either go onto one of the fluorine atoms, or they could go onto the central xenon atom. Now, from an energy perspective, it makes more sense to put that extra pair of electrons onto the central xenon atom rather than onto one of the fluorines, because number one, the xenon atom has available d orbital electrons as an element in period 3 or above, where we can place those electrons. And number two, by putting those electrons on the central atom, that is the larger radius central atom, the repulsion between those electrons and the other remaining electrons as part of that electron cloud is minimized. Whereas if we put those electrons around one of the smaller fluorine atoms, that would greatly increase the repulsion between electrons and therefore increase the potential energy of our system overall. So if you ever find yourself in a position with extra electrons left over after having completed the octet rules, the general rule of thumb is to always place those extra electrons on the central atom, that is the large radius central atom, to minimize repulsion in your molecule. Now, having a look at our molecule of xenon hexafluoride, you'll notice that the xenon atom in the center has a total of 6 electrons in bonds and a lone pair of electrons, which gives it a total of 6 times 2 is 12, plus the 2 lone pairs is 14 electrons around that central atom in its valence shell. This is again what we refer to as an expanded octet, an atom which has more than the allotted 8 electrons in its valence shell. The reason why xenon is able to do this is because, as an element in period 3 or higher, it does have those extra d orbitals which are available to use in forming bonds. So the general rule of thumb for atoms which can do this are that they must be in period 3 or higher. So that is the only elements which can form expanded octets are in period 3 or higher, because period 3, or the third principal energy level, is the first place where we see the existence of those d orbital electrons, or d orbitals, available to help in forming bonds within these molecules. Next, we're going to go ahead and have a look at another example of a molecule that does not follow our octet rule. We're going to have a look at the species nitrogen dioxide, NO2. So just as before, we're going to follow our sequence of rules for determining the Lewis dot structure. Starting off, we're going to determine the number of valence electrons available to form bonds. Looking at nitrogen, an element in group 5 on the periodic table, we've got 5 valence electrons, and a pair of oxygen atoms, each of which has 6 valence electrons, gives us a total of 6 times 2 is 12. When we sum all of those electrons up, that leaves us with a total of 17 electrons in the valence shell with which we can form bonds. We're going to go ahead and draw next our skeletal structure, placing the nitrogen atom at the center of our molecule, as nitrogen is the less electronegative of the 3 atoms here. And we'll go ahead and put 2 single covalent bonds between the nitrogen and the oxygens on either side. In making those 2 single covalent bonds, we use up a total of 4 of our available electrons, leaving us with 13 remaining in order to fill our octets. At this point, we're going to go ahead and pause for a moment to make a comparison between the number of electrons we have available to form our bonds versus the number which we still need. Counting up, the oxygen on the left-hand side and right-hand side each need a total of 6 electrons to complete their octets, whereas the central nitrogen, with already 2 bonds, only needs at this point a total of 4 electrons in order to fill its octet. This gives us a total of 6 plus 4 plus 6, 16 electrons which we need to complete our octets, versus a total of 13 available. Now, at this point, we recognize that there is not enough electrons to go around, which means, just like kindergartners had to learn how to do, if there's not enough to go around for everyone, we're going to have to share more electrons. So we'll go ahead and put a double covalent bond between the nitrogen and one of the oxygens. In forming another bond, we use up an additional 2 electrons, leaving us now with a total of 11 left to distribute. And at this point, we can go ahead and redetermine the number of remaining electrons necessary to complete octets for the rest of the atoms. So counting up, the oxygen on the left-hand side now needs only a total of 4 more electrons, whereas the central nitrogen only needs 2, and the oxygen on the right-hand side still needs a total of 6. So again, counting up, that gives us a total of 4 plus 2 is 6, plus 6 is a total of 12 electrons, which we still need in order to complete our octets. At this point, we have to recognize that this is really, at this point, as good as it can be in terms of being able to fill the octet rule for every single atom. Because with an odd number of electrons, it is fundamentally impossible to fill the octet for each single atom. So at this point, we need to start distributing our lone pairs of electrons, recognizing that one of the atoms is essentially going to be shorted by 1 electron. And in order to determine which of those atoms we're going to give an incomplete octet to, we have a choice essentially here between nitrogen and oxygen. Because nitrogen is less electronegative than oxygen, it has a weaker ability to attract those electrons to itself, and as such, we would expect nitrogen to be the element which in this case would end up with only a set of 7 electrons in its valence shell. So at this point, we can go ahead and distribute those electrons, completing the octets for the oxygen, and then leaving nitrogen as an exception to our octet rule here with only a total of 7 electrons. And again, we call this an odd electron exception. The species which are most likely to do this are nitrogen or phosphorus. So please make sure you're on the lookout for those as you go to work your homework problems and work the test. And at this point, we've got one more example of a species that does not follow the octet rule. This particular species is BCl3, boron trichloride. Just like before, we'll start off by determining the number of available valence electrons with which to form bonds in this molecule. Boron is an element in group 3 on the periodic table, and therefore has 3 electrons available. Chlorine as a halogen has 7 available electrons in its valence shell. We have 3 of those chlorines in the BCl3 molecule, for a total of 7 times 3, or 21 electrons. When we sum up those values, this gives us a total of 24 electrons in the valence shell available to form bonds. As the less electronegative element, we're going to go ahead and place boron as our central atom, and then distribute the 3 chlorine atoms around the outside as our peripheral atoms. And we'll go ahead and now draw our skeletal structure with single bonds between the boron and each of the 3 chlorines. In making those 3 single covalent bonds, we use up a total of 6 valence electrons. Subtracting those from the 24 we had available to start gives us a total of 18, with which we can now use to complete our octets. And at this point, we have to recognize that in a normal situation, we would go ahead and form a double bond between the boron and the chlorine, recognizing that in order to complete our octets, each of the chlorines still needs 6, and the boron still needs 2. So that means we have, again, 18 electrons available, but 20 which we need to complete the octets. But here's the trick. Because chlorine is so much more electronegative than boron, chlorine is not going to really have a strong tendency to form a double bond, that is to share more electrons with boron, because again, chlorine is better at holding on to its own electrons as a much more electronegative species. And this brings up one of our examples of the exceptions to the electron configuration rules. Rather than going through and completing the octet for each of the atoms by forming a double bond, instead, we're going to go ahead and distribute all of the lone electron pairs to the chlorines, leaving the boron as an electron-deficient species. And at this point, we call this an incomplete octet. That is, boron only has a total of 6 electrons around it in its valence shell now. But again, remember, the reason why we form these bonds is not in order to complete octet rules, but to put those electrons in their lowest potential energy level positions. Because the boron is less electronegative and the chlorines are much more electronegative, from an energy standpoint, it makes much more sense to put the lone electrons around those chlorine atoms at a lower potential energy position than it would be to form an additional bond between the boron and the chlorine. And again, the types of atoms that tend to form these expanded octets, incomplete octets, in addition to boron, is the other element right next door to it, which is beryllium. Boron tends to be stable with only a total of 3 bonds. Beryllium tends to be stable with a total of only 2 bonds. And at this point, we've discussed all of the exceptions to the electron configurations we need to deal with here. So you can go ahead and spend some time working on the homework set, which is problem set 414 on exceptions to the Lewis dot structure rules.